Let's continue from slide 19 of Phys 8 Slides 08.pdf. So now we're finally getting chapters and days out of sync. This will be to prepare you for day number 9, where we'll do worksheet number 9, but it's going to cover the rest of chapter 8. And for the moment, I'm going to keep the slide file numbers matching the Mazur chapter numbers. So it's Phys 8 Slides 08.pdf. So let's start talking about springs. So the equation that describes springs is Hooke's law. Okay, and so when you pull on a spring, it stretches. And if you stretch a spring, the spring pulls back on you. And then if you compress a spring, oh, maybe I should draw that too. If you compress a spring like that, so here I'll draw my hand here. I didn't plan on that. So there's my hand compressing the spring. So if I compress the spring to a shorter length than its equilibrium length, then it's going to push back on me. So what I've kind of tried to draw here is, here's the spring at its relaxed length. Okay, let's say x0 is its relaxed length. And this would be like x equals 0. So this x is x equals x0. And then x increases this way. And here I have pulled the spring out to the right. So I've increased the end of the spring from x equals x0 to x bigger than x0. And therefore the spring is pulling back on me. Okay, so the force exerted by the spring on me, if I stretch the spring to a length longer than its equilibrium length, then the spring is trying to pull itself back to its equilibrium length. Its relaxed length. I should say its relaxed length. So in this case, if I pull the spring so that the end of the spring is at x bigger than x relaxed, then the force exerted by the spring on me points in the minus x direction. If instead I squish the spring so that x of the end of the spring is smaller than the relaxed length of the spring, then the spring pushes in the plus x direction on me. Okay, so of course, yes, I'm saying what the spring is doing to me. Here the spring is pulling me to the left. Here the spring is pushing me to the right. So the force by the spring on me, see, if x is bigger than the relaxed length, then it points in the minus x direction. And if x is smaller than the relaxed length, then it points in the plus x direction. So people every year ask about the minus sign. The minus sign is just to help you keep track of what direction is the force exerted by the spring on me. So if I make the spring longer than its relaxed length, the spring itself pulls in such a way as to try to make itself shorter. And if I make the spring shorter than its relaxed length, then the spring itself pushes in such a way as to try to make itself longer. So if you just think about that, then I think you can work out the science. And this is again where these free body diagrams help, because then you can draw arrows and you can think about whether the arrows make sense. So there is a constant of proportionality called the spring constant. And so it's basically, you could call it the stiffness of the spring. So if I can stretch a spring very easily, if I can stretch it a long way without a very big force, then there's a small spring constant K. And if it's really difficult for me to stretch the spring even a little bit, or compress the spring even a little bit, then that's a big spring constant K. So a bigger K is like a stiffer spring, and a smaller K is like a less stiff spring. So we actually are just taking the spring constant K kind of as a given right now, but when we talk later about the properties of building materials, then we'll see where the spring constant K comes from in terms of properties of the material and like the dimensions of the material. And again, the minus sign indicates that if I make the spring longer, the spring tries to become shorter, and if I make the spring shorter, the spring tries to become longer. So what the spring is trying to do is kind of the opposite of what I do to the end of the spring. So that kind of is where the minus sign comes from. Okay, let's look at a video clip with some examples of springs. So this scale reads out in newtons, It reads a pretty small number right now, and I can make the spring longer and longer, and as I make the spring longer and longer, the force read out gets larger and larger, and it should be in proportion to how much I elongate the spring with respect to its relaxed length. This is the relaxed length of this spring, and when I apply a force to the end of the spring, its length changes from the relaxed length, in this case, to a longer length. And so it's that difference, the new length minus the old length, times a thing called the spring constant. So the Hooke's law spring constant, K, times the new length minus the relaxed length, equals, in magnitude, the force between the end of the spring and what's connected to the end of the spring here. Initially, the bottom of this spring is pretty well lined up with this clip. And then let me put a ½ kilogram mass on the end of the spring. So that's 5 newtons of force. And we'll see how far it stretches. So it seems to stretch about that far. Okay, we'll bear that in mind. And now let's instead use a 1 kilogram mass. That's about 10 newtons of force on the spring. And we see that with twice the force applied, it does seem to stretch about twice as far with respect to the original position. So we started out here. Here's where we were after 5 newtons, and here's where we are after 10 newtons. It seems to be about twice as far. That's pretty good. The bigger the spring constant, the stiffer the spring. So here's a spring which is much less stiff than the original spring, and they have pretty similar relaxed lengths. So let's see what happens when we put a 1 kilogram bob on the end of this spring. You can see how far the end is displaced. Let's put a 1 kilogram bob on the end of this spring. Whoa, look at that. So here's a ½ kilogram bob on the first spring, and then this spring apparently is less stiff than the first spring. So we'll put a ½ kilogram bob on this spring, and it appears, well, how different is that displacement? It seems as if the displacement of the end of the first spring is, let's say, roughly 10 centimeters. And by contrast, the displacement of the second spring seems to be, let's say it's roughly 60 centimeters. So I would say this spring is about 1/6 as stiff as this spring. So that means that the spring constant of this spring is about 6 times smaller than the spring constant for this spring. I think we have here an example of a stiffer spring than our original spring. So I'll try to stretch these by about the same amount, and it seems as if the force exerted on the scale by the stiffer spring is, yeah, it's roughly twice the force exerted on the scale by the less stiff spring. So I think these spring constants are about a factor of 2 apart in magnitude. So this is a stiffer spring, this is a less stiff spring. And then this was an even less stiff spring than this. A spring hanging from the ceiling is 1 meter long when there is no object attached to the spring's free end. So here is my copy of the spring with nothing on it. And here's x equals 0, and here's x equals -1 meter. I decided to make the x-axis point upward just because we've been doing that for a while. And I think when I, in the past, have made the x-axis point downward, it has confused everybody. So let's make the x-axis point upward. And so I guess this is our first spring problem working out together. So when a 4 kilogram brick is attached to the free end of the spring, the other end is attached to the ceiling, then the spring becomes 2 meters long. Okay, so that means the end of the spring, instead of being at -1 meter from the ceiling, it's going to be at -2 meters down from the ceiling. So what is the spring constant of the spring? And I guess to figure this out, the hint is we want to draw a free body diagram for the brick and figure out what magnitude force the spring must be exerting on the brick. And the idea is that the brick is just sitting there, so it's not accelerating. The magnitude of the force exerted by the spring is the spring constant times how far the spring is stretched with respect to its relaxed length. Let's work this out. So a free body diagram for the brick. So here is the brick, and I guess we're going to say brick, which is B, and here I'll do it kind of like the Eric diagram method. So you're kind of indicating that this is what you're drawing a free body diagram for. And okay, so the brick is an object that exists near Earth's surface, and it has a mass, so it's going to have there's going to be a gravitational force. So we remember, for the free body diagram for the brick, we want forces acting on the brick. So we have the gravitational force exerted by Earth on the brick, okay? And that equals the mass of the brick times little g. And then we have upward, and these are going to be the same length because the brick, I guess B is the brick. The brick is not accelerating, okay? So this is the force I don't know whether to call it an elastic force or a contact force. I'm going to call it a contact force. It could be an elastic force or a spring force. Sometime later we might call it a spring force or an elastic force. For now I'll call it a contact force because the spring is contacting the brick. This is the spring on the brick. Oh, and its magnitude. So we only want its magnitude. It's pointing up. So its magnitude is K. Well, actually, it's really K times, I guess, like the absolute value, oh gosh, of, let's say the absolute value of x minus x0. Now I'm going to confuse you again. I'm just writing its magnitude. So let's actually write x components. Actually, you know what I'm going to say instead? I'm going to say the x component of this is minus the mass of the brick times g. And I know you're not going to like the absolute value thing. So I'm going to say the x component of this is minus k times x minus x relaxed. So that is a true statement. So x is smaller than x relaxed. So that means x minus x relaxed will be negative, and then we multiply by the minus sign. That'll give us a positive value, so then it makes sense that it points up in the plus x direction. Okay, I think that's good. And now because we say that this brick is in equilibrium, so the vector sum of forces acting on the brick is 0. There are only two forces, and the brick is not accelerating, so the two forces must point in the opposite directions, and they must be the same magnitude. So I'm going to draw a little hash mark like that to indicate these two arrows are the same length. So then, what that says, you see, often you can use a free body diagram to write down Newton's second law. And that's like the mass times acceleration is the vector sum of forces, or the mass times the acceleration. Newton's second law is the mass times the x component of the acceleration is the vector sum of forces in the x direction. And this is, let's say, the mass of B, and it's the acceleration of object B. Then these are forces exerted on B. But in this case, the acceleration is 0. So we don't have to worry about the acceleration. The acceleration is just 0, so we know the forces, the x components of the forces must add up to 0. So we can say that minus the mass of the brick times g, and then we can say minus, because I guess we're adding them, although this will end up being, the minus signs are a little silly, but I'm going to try to be very formal for the moment. There's a spring constant, and then this is x minus x relaxed equals 0. Okay, so I guess I could go through and cancel both minus signs because there's no point having two minus signs here. So I'll do that. And then you can notice that x is actually smaller than x0. So in fact, I could say that the mass of the brick times little g equals the spring constant times x relaxed minus x. And I'm just doing that because I know that x is smaller than x relaxed. So then this is saying that 4 kilograms times 9.8, but I guess the problem says use 10. You could say newtons per kilogram is the same thing as meters per second squared. And so then this is going to equal k times minus 1 meter minus 2 meters. Which is, okay, so this tells you that 40 newtons equals k times 1 meter. Because minus 1 minus 2 is 1. Okay, so then that gives us that the spring constant, k, I guess I'll put this up here. This gives us that the spring constant, k, is 40 newtons per meter. Okay, so there is our answer. Let's see if that corresponds to any of our choices. Oh, here we go. So this is choice E, echo. So the spring constant is 40 newtons per meter. Now we could have done all that kind of in our heads, but you want to be systematic at first, and then once you get good at this, sometimes you can save yourself a few steps. So you say, okay, 4 kilograms, that's about 40 newtons, right? I mean, you could say times 9.8, but I'm going to say 40 newtons. So you're pulling, there's a force of 40 newtons, and then the change in length is 1 meter. So that's 40 newtons per meter, because the change in length is a meter, and the force is 40 newtons. So that's 40 newtons per meter. So you could have done it in your head, but it's nice to be formal when you're starting out so that you can see the reasoning behind the conclusion that you reach. Okay, that was our first spring problem. So suppose you want to measure your weight with an old-fashioned spring scale, like an old-fashioned bathroom scale that works on a spring mechanism. So most bathroom scales work something like this. So imagine that this is actually like a laboratory jack, but let's pretend it's a spring. So you just saw what happens when you suspend a brick from a ceiling-mounted spring. So instead, let's have a spring sit on the floor, and then here is its relaxed length, and then I step on it. When I step on it, the spring squishes. And if we know the spring constant, we know how much the spring squishes, then we know how big the force is that the spring is exerting on me. And if I am not accelerating, then we know by implication how big the force is that I am exerting. Well, let's see. Maybe we should draw a free body diagram for me, actually. Okay, let me just talk it through, and then maybe we'll draw a free body diagram. So here's the spring. It's at its relaxed length. I step on the spring, which is the bathroom scale, and it squishes a little bit. And so then the force that it exerts on me is upward and is in proportion to how much I squish it. So it's like the spring constant times how far did I squish it by is the magnitude of the upward force exerted on me by the spring. The spring is the scale. And then meanwhile, Earth is exerting a downward force on me, gravity, which equals my weight. So if I'm not accelerating, then the upward force exerted by the spring on me must be equal in magnitude to the downward force exerted by Earth on me. And both of those forces therefore equal my weight. So the scale can then tell you what is my weight because it knows how big a force it's exerting on me. And the way it knows that is that it knows how much it has squished. So the scale knows how much it has squished. It takes how much it has squished times its own spring constant. That's the force it's exerting on me. And if I am not accelerating, then the force the spring is exerting on me must be the same magnitude as the downward force that Earth is exerting on me. And the downward force that Earth is exerting on me is my mass times little g. In other words, it is my weight. So then the scale tells me my weight. Now, here is the tricky part. What happens if, in fact, we are doing this on an elevator? So I told you I was not accelerating. Well, what if in fact I am accelerating? Then what value does the scale read out? Let's think about that. A bathroom scale typically uses the compression of a spring to infer the gravitational force, mg, exerted by Earth on you, or on me, which we call your weight, or my weight. Suppose I am standing on such a scale while riding an elevator. With the elevator parked at the bottom floor, the scale reads 700 newtons. Okay, so that means I would weigh about 70 kilograms. I would have a mass of about 70 kilograms, so my weight would be about 700 newtons. I push the button for the top floor. The door closes. The elevator begins moving upward. At the moment when I can feel, like in my stomach, I can feel that the elevator has begun moving upward, what does the scale read? Okay, so let's start by drawing a free body diagram for me. Okay, so here's me. Here I am. And I'm standing on the scale. This is the scale. And then here is the floor of the elevator. And all of this is happening inside an elevator. Okay. And I want to draw a free body diagram. I guess I'm standing on the scale. I want to draw a free body diagram for me. Okay, so we'll say me. All right. I guess me will be M. How about that? Big M for me. So what are the forces on me? Well, we have a gravitational force, Earth, on me, which is mg. So my mass is m. My mass is m. And then we have, so if we're not accelerating, then we have a contact force by, okay, so the scale is s, by the scale on me, and I guess it is, well, it's and then it's like k times x minus x relaxed, right? And then you could have a minus sign. I mean, the sign kind of indicates whether the force is up or down. I'll put a minus sign here, but I mean, okay. We kind of want the I usually draw the magnitudes and the arrows indicate the direction. So I always feel a little ambiguous about putting signs onto these arrows on free body diagrams because you kind of infer the magnitude from the direction from the arrows. Okay, so if we're not accelerating, you see, so if A is 0, then these two things are the same length. But now, we said you just feel that the elevator starts to move upward. So if the elevator a moment earlier was at rest, and now an instant later it is moving upward with a positive and upward velocity, and then, so if we have the x-axis pointing upward, then I guess we have a sub x is bigger than 0. Okay, so the elevator is accelerating upward because its velocity a moment ago was 0, and then an instant later or a short time later, its velocity is in the positive x direction. So that is a change in velocity in the positive x direction. That must be a positive acceleration in the x direction with the x-axis pointing upward. So now we no longer say that A is 0, and therefore we're no longer going to say that these two arrows are the same length. So, in fact, we don't know how long to make this arrow yet. So if we say that A sub x is bigger than 0, so then we'll say we're accelerating upward, then, well, does the gravitational force exerted by Earth on me change because I'm accelerating? No. The gravitational force exerted by Earth on me is still my mass times little g, whether or not I am accelerating. Yet, somehow, the vector sum of these two arrows has to point upward because I'm going to accelerate upward. So which arrow changes? I guess the arrow that changes is the force exerted on me, exerted by the scale on me. So that means now that the force exerted by the scale on me is going to be bigger in magnitude. So right, so this was 700 newtons. Actually, this is 700 newtons. So this equals 700 newtons. And this was 700 newtons, so now it's going to be bigger than 700 newtons. Make sure this looks like a bigger. Because somehow that orange arrow has to be bigger than the magenta arrow. So I say that at the moment when I can feel the elevator has begun moving upward, the scale reads a value larger than 700 newtons. And we might have a video clip of that. I guess another interesting thing to think about is what happens if the elevator accelerates downward. So what does happen if the elevator accelerates downward? So if the elevator were to accelerate downward instead, so then we would have a sub x is less than 0. So this is like when the elevator, well, it could be that the elevator is parked on the top floor and it starts going down, or it could be that you are almost at the top floor, so the elevator has to slow down. It's going up and it's slowing down, therefore it's accelerating downwards to arrive at the top floor. So in that case, so if the elevator is accelerating downward, so then you'd have a sub x less than 0, so the acceleration is downward. Then again, this arrow doesn't change because the gravitational force between me and Earth doesn't change just because I'm accelerating. But now this arrow becomes shorter, so now this arrow would be smaller than 700 newtons. So this is now less than. So if I'm going to accelerate upward, then the scale has to push on me with a force bigger than my weight. And if I'm going to accelerate downward, then the scale has to push on me with a force smaller than my weight. So that one way or another, the vector sum of forces on me in the x direction equals my mass times my acceleration in the x direction. I guess we haven't tried to quantify this yet. I guess we could in a minute, but the answer we're going to get is that I guess we're going to say my mass times my acceleration in the x direction equals, so we can do up minus down because we have the x axis pointing up. So this would be, I guess we can say minus k x minus x 0. I think that's right. Because you see, when I step on the scale, x is going to be smaller than x0. So this actually is a negative number. This is a minus sign, but this is a negative number. So this value, this thing actually, this quantity here, this term actually is positive. It's just, it becomes less positive if I'm accelerating downward, and it becomes more positive if I'm accelerating upward. And then we'll say plus mg, my mass times g. So it's actually kind of interesting. We actually get that the this minus k times x minus x0, which I don't really like to write it that way because it looks like it's negative, but it's really positive. So this is the force in the x direction by the scale on me is actually my mass times a sub x plus g. So if I'm not accelerating, it just equals my weight, mg. And if I'm accelerating upward, you see it's bigger than mg. And if I'm accelerating downward, it's smaller than mg. So this is a positive number, even though this looks negative. It's a positive number because the number in parentheses is negative. But you can see it's bigger than my weight if I'm accelerating upward and smaller than my weight if I'm accelerating downward. Okay, I think we're going to redo that at some point. So let's talk about tension versus compression. So when a force tries to squish a spring, that's called compression or a compressive force. And when a force tries to elongate a spring, that's called tension or a tensile force. So we're going to spend a lot of time in a month or so talking about compression and tension in columns and beams and so on. But for now, remember that tension is the force trying to pull apart a string or a rope or so on. And compression is the force trying to squeeze a post or a basketball or a mechanical linkage or so on. Then there's an interesting thing about strings and ropes and so on, which is that they're floppy. So a string, unfortunately I don't seem to have a string here, but a string, you can stretch a string or a rope or a cable, but you can't really compress it. See, so it could be stretched apart, but it doesn't push back if you try to squish it. So there'll be an interesting thing about cables and ropes and strings with a T, is that you can put them in tension, but you can't put them in compression. They have no way to push back on you if you try to squish them. Whereas a spring can push back on you if you try to squish it. And like something like a mechanical linkage or a beam or a column or a bar or rod, can push back on you. So anyway, interesting thing about ropes, cables, etc. They can only have tension, they can't have compression. At this point in the course, I'm always tempted to say, hooray, we're finally talking about forces, because if you took physics before, then forces were introduced much earlier than they are in this course, and we've been kind of dancing around the term force until now. So finally, we can use the term force. So the force concept quantifies the interaction between two objects. Remember, forces always come in interaction pairs. So the force exerted by object A on object B is just the opposite of the force exerted by object B on object A. So they have the same magnitude, but they point in opposite directions. And this left side would appear in the free body diagram for object B, but not for A. And this right-hand object would appear in the free body diagram for A, but not for B. And then if you want to figure out how object A accelerates, you have to take the vector sum of the forces that act on A and divide by the mass of A. Now here's a way we haven't seen this yet. This is kind of a new way of talking about forces. The vector sum of forces acting on A equals the rate of change with respect to time of the momentum of object A. Or to put it into x components, the vector sum of forces of x component. The sum of the x components, the signed sum, of the x components of forces acting on A equals the rate of change with respect to time of A's momentum in the x direction. Okay, so force is the rate of change of momentum. Okay, so that's kind of an interesting thing. Force is the rate of change of momentum with respect to time. Here are a few kind of summary statements from the beginning of our discussion of forces. An object whose momentum is not changing is in translational equilibrium. Okay, so the word equilibrium will reappear in a big way later when we talk about the members of an architectural structure. So to achieve equilibrium, we want all forces acting on each member in a structure, let's say, to sum vectorially to 0. So typically, something is standing still and it's continuing to stand still, so therefore it's not accelerating. So then the vector sum of forces acting on that thing is 0. And that's going to be true for, things holding a building up, but it's also, it's often true in our little physics examples. So to put something in equilibrium, meaning it is not accelerating, then, translational equilibrium means it's not accelerating. Later we'll see that there's such a thing as rotational equilibrium also, but anyway, for now we have translational equilibrium, so it's not accelerating. we want the vector sum of forces acting on that object to be 0 for it to be in translational equilibrium. By the way, the unit of force is the Newton. And so when you say Newton as a unit, use a lowercase n. So 1 Newton is 1, and then capital N is the abbreviation. And a Newton is 1 kilogram meter per second squared. And that's because F equals ma, so Newton is F, and then here's m is kilograms, and a is meters per second squared. As we've seen, free body diagrams depict all of the forces acting on a given object. They're used all the time, by the way, in analyzing structures. So I think you'll really learn to like free body diagrams in this course. They actually are quite useful. The force exerted by a compressed or stretched spring is proportional to the displacement of the end of the spring with respect to its relaxed value, x0. So x0 is like its relaxed length, and then if you make it longer, then it tries to pull itself shorter, and if you try to squish it to be shorter, it tries to push itself longer. And this k is the spring constant. So k is measured in newtons per meter, because you change the length of the spring some number of meters, and it pushes on you some number of newtons. So here's our statement of Hooke's law. The force, the x component of the force exerted by the spring on the end of the spring is minus k times the position of the end of the spring minus the equilibrium position, not the equilibrium, the relaxed position of the end of the spring. It's sometimes common for people to call the relaxed length of the spring the equilibrium length, but that's really not correct, because once you suspend something from the spring, then things are in equilibrium at a different value. So be careful. The relaxed length of the spring. So the length of the spring when it's just floppy is its relaxed length. By the way, when a rope is held taut, that rope exerts a force which is called the tension on each of its ends. Okay, it's the same magnitude tension on each end. So this is kind of assuming a rope which has negligible mass. So the rope is exerting the same force on each of its ends, which just equals the tension. And actually, if you were like to cut the rope in half in the middle, then to hold the rope together in the middle, you would have to exert that same force, T, the tension, between the two ends that you just cut. Okay, so anyway, so there's typically like one force of interest in a rope, and it's called the tension, and you just have to figure out the direction. So like since a rope, you can't push a rope, you can only pull a rope. So basically, I'm pulling on this side of the rope with a force T, so the rope is pulling back on me with a force T. And then therefore this other side of the rope is pulling on my other hand with a force T, so I must be pulling on it with a force T. So it's kind of the same force T tension everywhere. It's really just one copy of T. It takes a little getting used to that. So we'll work a lot of examples that help us to get used to that. By the way, a large category of physics problems and even architectural structures problems like a suspension bridge involve two objects connected by a rope or a cable or a chain or so on. And these things, cables, chains, ropes, they can pull, but they cannot push. Okay, so there are two cables, for example, in this diagram. And I've drawn them both in yellow, so you can see there's one cable here which seems to be holding this beam to the wall and keeping it from falling down. And then there's another cable here which seems to be suspending this sign that says it's Joe's Auto Repair Shop. Okay, so we're going to work with lots of problems involving cables over the next couple months. Usually the cables in physics problems are considered light enough you don't have to worry about their mass. Okay, so we pretend the mass of the cable itself is 0. And usually the cables in physics problems are stiff enough that you don't have to worry about their stretching when you pull on them. So it's like a spring with an infinite spring constant. So like no matter how hard you pull on it, it doesn't stretch. So that's kind of our idealized physics cable. So the cable's job is just to transmit a force from one end of the cable to the other end of the cable. And again, we call that force the cable's tension T, capital T. So a cable always pulls on both ends with the same magnitude T. That's a cable where there's only something connected at each end. You can come up with more complicated situations, like a rope that's wrapped around a tree. We're not going to, okay, let's not worry about that. So if you assume that the cable is really just a rope straight out, or sometimes we have a cable that's like going over a frictionless pulley. In that case, it's still the same thing. It's pulling with the same tension on each end. Okay, so bear that in mind. So in the examples we'll do for the time being, a cable just simply transmits a force from one end of the cable to the other, and the magnitude of that force is T, the tension in the cable. I guess if you want to be formal, we're like neglecting the cable's mass, and the cable's acceleration must be finite to get this same magnitude on both ends. But let's ignore that last statement unless you really enjoyed a previous physics course. Okay, so for example, we can like suspend a basketball from the ceiling. Oh, let's try that. So we could here's a ceiling, and then we have a cable, and then we suspend a basketball from that cable. And then I guess you say the basketball has a mass m, so then there must be a tension T equals mg, assuming that the basketball is in equilibrium. Now the way I did that was kind of a shorthand, because if you were to draw a free body diagram for the basketball, you would say, aha, well, there is a gravitational force. This is the basketball. Basketball. Okay. There's a gravitational force exerted by Earth on the basketball, and that's the mass of the basketball times g. And then there's a contact force exerted by what is this thing called? A cable? By the cable on the basketball, and its magnitude is t. And then the acceleration is 0, so then you conclude that t equals mg, because there are only two forces, and they must be the same magnitude because the basketball is not accelerating, because it's just suspended there from the ceiling. Okay, so let's work an example now. Two blocks of equal mass are pulled to the right by a constant force, which is applied by pulling at the arrow tip on the right. The blue lines represent they're red lines. The red lines represent two identical sections of rope, which can be considered massless. Both cables are taut. Okay, both cables are taut. And friction, if any, is the same for both blocks. What is the ratio of tension 1 to tension 2? Well, my hint says it's worth drawing a free body diagram first for the two mass system, then for the left mass, then for the right mass. So let's do what my hint says. So let's draw a free body diagram for the two block system. So I'm going to make this horizontal since all the relevant forces are horizontal. So we have, I guess we have the frictional force, I'm going to say on the second mass. And then there's also the frictional force, which supposedly is the same, the frictional force on the first mass. And, then there is the force that I am pulling, which is, then there's basically who's pulling? Am I pulling? Well, it's not clear who this is. I'm just going to call it T. Okay, this is the tension. This is T1. So somebody is pulling on the first mass. I don't know. We can call it like the pull on the first mass. Okay. So those are all of the external forces. Okay, those are all of the forces exerted by stuff outside of the two-block system on the two-block system. So now, so that was for the two-mass system. Okay, now let's draw a free body diagram for the left mass. Okay, so the left mass, and I'm calling the left mass, I think, number 2. I guess I called the right mass the first one, and I called the left mass the second one because the tensions are ordered in that order, so what the heck. Okay, so now we need our little plus sign here. And what is happening to, this is for the second mass. Okay, so it seems like we have a tension. I don't know how big this is necessarily. I'll just draw it like this. This is, we'll call this T2. So, and what do you want to call it? You could call it the second rope. You could call it the first mass. I'm going to call it actually the contact force, or the, well, maybe it's a tension. I don't know. I'm going to call it a contact force by 1 on 2. Okay? Because really, what is the rope doing? The rope is really the way that block 1 pulls on rope 2. The rope is just transmitting the force from 1 to 2. So you could say it's the second rope on block 2, but sometimes I find it convenient to say the rope is the mechanism by which the first block pulls the second block. And the nice thing about that is it will become obvious in a moment that we have an interaction pair. Okay, then we have one of these little friction forces pointing backward. And I think, so this is, whatever this was, it's going to be another one of those, right? So it's the same thing. So this is the frictional force on the second. And we aren't really sure what that is. I guess it's like the whatever the table beneath is. So it's not obvious in this diagram what the forces are being exerted by. Like the frictional force must be by this surface down below, and then this first pull must be by whatever's pulling on the arrow, but that wasn't identified. So, and okay, they're being pulled to the right by a constant force. And we actually don't know whether things are accelerating or not. Okay, so that's that. So we're still looking. And then, and we actually don't even know for sure whether the system is accelerating. So I think we're going to say A sub x is question mark. We actually don't know what A sub x is. We actually don't even know the direction. But because the cables are taut, if block 1 is accelerating, then block 2 has the same acceleration. So because the cables are taut, whatever the acceleration is, it might be 0, whatever it is, it seems like it's the same for both blocks. Also, I think this argument only works if the acceleration is either 0 or to the right. If the acceleration is to the left, there could be a problem because I don't know if the cable would still stay taut. Okay, so let's now draw, so that was the left mass. Now let's draw a free body diagram for the right mass, which I'm calling number 1. So here's my little X sign, and so I have, this is the same arrow that I drew up here. So this is really T1, which is, I don't know, it's like whatever is pulling on 1. That's not a very good Eric Mazur style label, but we weren't told what the origin was of that force. And then we have a frictional force, and we're told that if there is any friction, we might as well assume there is. If we said we don't know whether there is or isn't, then it's the same for the two blocks. So then here is the frictional force on number 1. And we actually, again, the acceleration, we don't know what it is or even whether it's non-zero, but I guess it's probably not negative. How are we going to figure out the ratio of T1 to T2? Now that's pretty interesting. So when you draw one of these free body diagrams, it lets you write down Newton's second law. So let's write down Newton's second law for, well, I guess we can say for the system as a whole. What the heck? Oh, I missed a force on number 1. Oh my goodness, I am embarrassed. So there is a second force. There's also, you see, if 1 is pulling on 2 to the right, then 2 must be pulling on 1 to the right. So this is T2. So this is the contact force by 2 on 1. It's basically through that rope. So whatever magnitude this is, this has to be the same because this force and this force are an interaction pair. Okay, so actually, I think these first two diagrams are going to be very helpful. So if we use this first diagram to write down, well, let's start here. Let's start in the middle. So this middle diagram lets us write down Newton's second law for this left-hand mass. So we can say m2, which is just the same m, times a sub x2 equals the vector sum, well, of forces in the x direction. So this is T2 minus 1 force of friction. Okay, then the forces of friction are the same, whatever they are. Okay, so I think that's useful. And then, that's good. And then over here, we can write for this two-block system that the whole system, m1 plus m2, that's the mass of the whole system, times a sub x of the system, but they all have the same acceleration, by the way. So, like, if the cables are taut, then if whatever the acceleration is of one block, it's the same as the acceleration of the other block, and it's the same as the acceleration of the system center of mass. So this is actually the acceleration of the system center of mass, but because they're staying fixed with respect to one another, it's the same as the acceleration of this block. It's the same as the acceleration of this block. So this is, so we're going to, we have our x-axis pointing to the right. So we'll say right minus left. So this is T1 minus, and we have 2 of these frictional forces. So it's 2 FF, because we said if they're non-zero, they're the same. So actually, this says 2m a sub x is T1 minus 2 frictions. And this one said that, see, m2 just m a sub x is T2 minus 1 of these frictions. So we can turn this around, and this tells us that T2 is m a sub x plus 1 force of friction. And T1 must be 2m a sub x plus 2 forces of friction. So this is the same thing as just 2 times T2. So I guess T1 must equal 2 times T2 because, yeah, so T1 equals 2 T2 because this expression that we wrote down for T2, and then we have this expression we wrote down for T1, and this expression we wrote down for T1 is just 2 copies of the same expression we wrote down for T2. So T1 must equal 2 times T2. So I think I like answer D here, that T1 is 2 times T2. Now let's think about why. Why did I ask us to write down a free body diagram for the front mass? I guess it was so we can look at it and see if it makes sense. So first of all, you see we have this interaction pair. This is tension 2. So it's like the contact force by 1 on 2 points to the right. The contact force by 2 on 1 points to the left. And they're two sides of the same force. So that's if you look at the rope as if it's something just communicating a force from one thing to the other, which I often do look at a rope that way. And then you could say, well, here's T1 and here's T2. And I guess if we wanted to, we could say, what is T1 minus T2? So I guess T1 minus T2 is just the same as T2. Okay, so what is this saying? This is saying that this mass, which is just m, right? So the mass of this guy times a sub x, and it's the same acceleration. This has to be T1 minus T2 minus this one of these forces of friction. And does that tell us? I'm sure it doesn't tell us anything new. I guess we can ask whether it tells us anything consistent with what we saw before. So this is T1 minus T2 is just m a sub x plus the force of friction. And, oh, and then minus the force of friction, right, see? So T1 minus T2 is just m a sub x plus the force of friction. And then we subtract the force of friction, and that is just a tautology. Yeah, so if you have, so this third equation just gave us a consistency check on the first two equations. So there's no new information in it. Okay, so maybe that just confused you, what I did with the third equation. But one thing that's kind of interesting about this third equation is it tells you, it shows you this interaction pair. It turns out, by the way, if you have a system like this that's being pulled from the right-hand side, usually the easiest way to approach it is to start at the far end and work your way up. And similarly, we'll see if we have a system of things that are like suspended from the ceiling and you want to figure out all the forces, you usually start from the bottom and work your way up. So typically if you have a bunch of things connected by ropes, you usually start from the far end and work your way up. And usually you save yourself some math that way. 3 blocks of equal mass are pulled to the right by a constant force. The blocks are connected by identical sections of rope, which can be considered massless. All cables are taut. So if all cables are taut, that means that if they're accelerating, they're all accelerating together. And friction, if any, is the same for all blocks. What is the ratio of T1 to T2? Ooh. Well, okay, so if they're all the same, if the friction's the same, the masses are all the same, you see T1 is pulling 3 blocks, T2 is only pulling 2 blocks. So I think T1 is probably going to be 3/2 of T2. That's going to be my guess. T1 is going to be 3/2 of T2. But let's see if we can work it out. So I claim that you usually want to start from the back and work your way forward with these things. So let's start with, here I'm going to call this 3, 2, 1. So let's start with block 3. So block 3 has T3 going to the right, and that's it, okay? So then we could write m a sub x. All these blocks have the same acceleration since the cables are taut. Is, oh, sorry, that's not it because there's the friction. Okay, there's the friction. Is T3 minus the friction force. Okay, then we can say, okay, how about block 2? So block 2, we have T2 to the right, and we have T3 to the left. And by the way, this and this form an interaction pair, basically, because this is essentially, I could be more careful, this is kind of like the this is the contact force of 2 on 3. And this is the contact force of 3 on 2. Okay, so that's another way you could write that. And then this is the contact force of 1 on 2. That's not very easy to read. And then there's a friction force backward. So we'll say, okay, here's a friction force on 2, and this is a friction force on 1. And again, we're not told exactly what's exerting the friction force. It's whatever that surface is underneath. And then we can draw one for block 1. So we have block 1, and here we have T1, and well, we don't actually know what that is. That's like the pull force on 1. And then we have T2 going backward here. This is T2, which is the contact force by 2 on 1, arguably. So then that makes this and this an interaction pair, if you think about it that way. And then there's 1 unit of friction force on 1. And all these friction forces are the same, we are told. And we actually don't know the accelerations, so I'm not going to write acceleration arrows because we don't know what the accelerations are. But now we can write Newton's second law for block 2, and they're all the same mass. So here's m, and they all have the same acceleration. ma sub x equals T2 minus T3 minus a friction force. And then what are we going to do for block 1? We could write Newton's second law, and that would be, and again, they're all the same mass, and they all have the same acceleration. ma sub x is T1 minus T2, and then minus a friction force. And is this helpful? Well, it seems like T3 is 1 mass times acceleration plus 1 unit of friction force. And then it seems like T3 is, let's move this over to this side. Oh, this isn't going to tell us T3. This is going to tell us T2. Sorry. This is going to tell us T2. So writing Newton's second law for block 2 will tell us T2. That makes sense. So T2 is going to be ma sub x plus 1 unit of force friction, and then plus T3. But notice that this is already what T3 was. This is basically saying T3 plus T3. So this is 2T3, because you see these first 2 terms are just the same thing as we wrote here for T3. So we're basically saying T2 is T3 plus T3. So that's like twice T3. Then let's write Newton's second law for block 1 here. So, well, we did. So let's solve this. So this gives us T1 equals ma sub x plus a unit of friction, right? Because we move this over to the other side, and then we can move this over to the other side, plus T2. Now, you see, this thing is the same thing as T3. So this is like saying it's T3 plus T2. So that's like T3 plus T2. And T3 was just, T2, yeah, that's like T3 plus T2. And T2 was just 2T3. So this is 3T3. There you go. So it seems like what we determined is that T2 is 2T3, and T1 is 3T3. So that tells me that T1 must be 3/2 of T2. That was kind of interesting. T1 must be 3/2 of T2. Yeah, times 3 divided by 2. And that kind of made sense from intuition, because you say, well, T1 is pulling all 3 blocks, whereas T2 is only pulling 2 blocks. And if all the blocks are the same and all the other forces on the blocks are the same, then it kind of makes sense that this is 3 units of force and this is 2 units of force. So that was kind of interesting. While we're here, let's also ask, what is the ratio of T1 to T3? Well, we actually worked that out along the way. T1 is 3T3. So I think I like that, foxtrot. So T1 is 3T3. Cool, so we got an answer to a second problem for free. Next, I'm going to show you a video clip of a device called an Atwood machine. This contraption is called an Atwood machine, and it basically consists of 2 masses. So I'm going to call them M1 and M2, and there is a cable that connects the 2 masses, and that cable goes up over a pulley. So the pulley itself is of negligible mass, and the cable is of negligible mass, and the pulley has negligible friction. Okay, now you'd say, if there's no friction in the system, then why aren't these things accelerating? And actually there's going to be a worksheet problem, which is in a slightly more complicated, enhanced version of an Atwood machine, adding a spring to keep things even more interesting. So we're going to see the Atwood machine sitting here just like this. 5 kilograms here, 5 kilograms here, 5 kilograms here, and this is a cable. So the cable just goes from M1 over a pulley and down to M2, and this is, let's say it's a massless, frictionless pulley. Okay, so it's a pulley that all it does is just keep the rope sliding over it. So it could be that it's like perfectly greased, you know, or it could be that it's just extremely lightweight and it has very good ball bearings. But in any case, the only purpose of that pulley is just so that you wrap the force around. So that whatever tension is pulling up over here, that same tension is pulling up over here. So if this is 5 kilograms and this is 5 kilograms, then, okay, first you could ask yourself, why are the 2 masses not accelerating? Well, actually, this is kind of like an elevator with a counterweight in a building. You say, well, if this is 5 kilograms, then let's call that 50 newtons, right? So there's a gravitational force of 50 newtons, and there's a gravitational force here of 50 newtons, the weight of that block. Now, I'm not being careful yet. I'm not drawing a free body diagram for anything. But I guess you'd say, well, those 2 50 newton forces balance each other. I guess it's 49 newtons if you use 9.8, but let's use g equals 10 to make the math easy. So it seems like, okay, you know, the 2 weights balance, so it kind of makes sense that they're not accelerating. So now if we do that, they're stationary and the 2 masses are equal. What is the tension in the cable? Now this is interesting. You might try to argue that the tension in the cable is 100 newtons, you know, because you have 50 plus 50. That would be a wrong argument. Don't do that. Don't do that. The tension of the cable is 50 newtons, because we say, what does the tension in a cable mean? You know, you have a cable and it has some tension in it, T. Well, the cable is pulling the same amount, just in opposite directions, on the 2 ends. So this tension in the cable equals how much force it's exerting on one side, and it equals how much force it's exerting on the other side. So it's just one tension. So bear that in mind. So the tension in this cable right now, if these masses are just, they're the same mass and the system is just at rest, the tension in the cable is 50 newtons. I mean, you want to be precise, it's 49 newtons, but it is 50 newtons in this case. Okay, so think about that a little bit. Now, if I make one mass 5 kilograms and I make the other mass 5.1 kilograms, oh, what's going to happen? So let's think about that. So if I make this mass be 5.1 kilograms, and this one is still, it's 5.0 kilograms, then I have 50 newtons down over here, and I have 51 newtons down over here. You say, well, gee, that's a little bit confusing because I thought you said the tension was the same on both sides. What's happening? Well, I think what's probably happening is that the system's going to accelerate. So you see there's a big, it's like you're pulling harder on the right side, you're pulling less hard on the left side. So I think the system is now going to accelerate this way. And as a matter of fact, to try to work that out, I'm going to use a really tricky coordinate system. So I'm going to say that over on this side, the x-axis points up. And over on this side, the x-axis points down. That's kind of tricky, but the reason I say that is so I can use the same variable, x, to represent the motion upward of mass 1 and the motion downward of mass 2. And the reason that makes sense is the cable is going to stay taut. So you know that if 1 moves up a little bit, 2 will move down by that same amount. The cable remains taut, so its length doesn't change. So if M1 goes down by 1 meter, then M2 must go up by 1 meter because the length of the cable doesn't change as we go along. So let's see if we can work. So the question is, if I make one mass equal to 5 kilograms, the other equal to 5.1 kilograms, what's going to happen? I think the system is going to accelerate in such a way that mass 2 moves down and mass 1 moves up. And how big is the acceleration? Now that's tricky. Let's see if we can work that out. And then, okay, so now if you pause that thought for a minute, suppose I make one mass 5 kilograms and the other one 6 kilograms. Will the acceleration be larger or smaller than in this case? Well, I think if the two masses are the same, the acceleration will be 0. And I think if I make M2 bigger than M1, then the acceleration will be such that M2 goes down and M1 goes up. And I think that the bigger I make that, it seems like if I make this asymmetry between M2 and M1 even bigger, I would think I would get a bigger acceleration. But how so? If I add a 200 gram mass to M1, so now this is 3.73, so this would become 3.93 kilograms, and this is still 3.73 kilograms. Watch what happens. So there is an acceleration, but the acceleration is small enough that it's pretty easy to see with the unaided eye. And if instead of adding 200 grams, I add 400 grams, you'll see that that acceleration is a little bit bigger, well, about twice as big. Okay, and let's say we add about 600 grams of mass on this side. Then if I let go, so, oh, and by the way, there's yet another way to think about this, which is just a little off to the side digression, which is if I were to, if I make this 5 kilograms and I make this, let's say 6 kilograms. So now this becomes 60 newtons. Then if you think about what happens if I raise the 6 kilogram mass by 1 meter and then the 5 kilogram mass goes down by 1 meter, well, that's interesting. So it seems like I have here's like mg times 1 meter up, and then I have mg times 1 meter down, right? So I have like, it seems like if I do that, I have m2g delta x, where let delta x be 1, well, I'm going to say 1 meter. m2 times g times 1 meter. And then I have minus m1 times g times 1 meter. So it seems like my change in gravitational potential energy in that case is m2 minus m1. That's interesting, times g, times however far I moved it, like I moved it 1 meter. And again, this is where I'm moving the 6 kilogram object up. So it seems like I can increase the gravitational potential energy of the system that consists of Earth and these two masses. If I move the more massive one up and the less massive one down by the same amount, then I'm increasing the gravitational potential energy by m2 minus m1 times little g times how far I moved them. So that's kind of interesting. We'll just file that fact away for a moment. So let's step back and draw a free body diagram for mass 1. Okay, so here is our free body diagram for mass number 1. I'm going to say it's for number 1. And it seems like we have a downward force, which is the force gravitational by Earth on 1, and that equals m1 times little g. And then we have an upward force, which is the tension. And you could say even that that's the contact force by 2 on 1, if you like. I don't know, you could say that. Maybe I'll just say it's the tension. I'm just going to say it's the tension. I don't want to give it a name. And I think, at least in our, where we said m2 is bigger than m1, we're going to say the acceleration is this way. And for this diagram, the x-axis points up. And then the other side, let's do a diagram for number 2. So this is for mass number 2. And we have the gravitational force by Earth on 2, which is m2 times g. And we have, now we have an upward tension. It's a little bit, now, you see, it's because the rope bends around, so we change the direction of the end of the rope by bending it around the pulley. So this is the same tension. So this turns out to be the same as this, because it's the same rope, it's the same tension. And then this one we said is accelerating downward, and then somewhat confusingly, our x-axis is pointing downward for this diagram, because that's our convention, so that the masses move together and they can be described by a single x-axis. I think that's good. So there are my 2 free body diagrams. So I claim we can write one equation for each of these 2 diagrams, and we have 2 equations and 2 unknowns. The 2 unknowns are the acceleration and the tension. But before we do that, let's just move ahead a little bit. By the way, I have 2 comments. One is this machine was originally invented as a mechanism for measuring little g and for studying motion with constant acceleration. So we're going to see that the acceleration that we get can be, if you adjust the masses just right. So if you have big masses, but they differ by just a little bit, you can get a very small acceleration. So that makes the motion small enough to study. And then the same concept is used as by the counterweight in an elevator for a building. So that's kind of convenient, because then if the brakes fail, then you're not going to have a gigantic acceleration at g. It'll be a small fraction of g. So it also makes it a little bit easier. We'll see you don't have to lift the whole weight of the elevator. You only really have to lift the difference in weight between the loaded car with passengers and the counterweight. Oh no, something bad happened. I didn't look ahead, and in my slides I said let's make m1 bigger than m2, and therefore it's going to then m1 is going to accelerate downward, so I made the x point the other way so that the acceleration will be the positive x direction. Let me fix that. Okay, I fixed my diagram on the board so that it looks like the diagram in my slide. So now m1 is bigger than m2. So how would we solve for the acceleration? So why don't you think about how you might do it. But here's how I think I would do it. I think I would say, I would take this diagram number 1 here, and we're going to say the x points down, so I'll keep x, so I'll say m1 a sub x equals, so the x direction, so positive minus negative. This is m1 g minus the tension. And then let me take this diagram, and the x-axis points upward, so, okay, m2 a sub x, and it's the same a sub x because the cable is taut. And so I'm going to take positive minus negative. So this is the tension minus m2 g. Now I have 2 equations and 2 unknowns, the tension and the acceleration. So I could then eliminate the tension by saying T equals m2 a sub x plus g. Yeah. And then I can say m1 a sub x equals m1 g minus m2 a sub x plus g. That seems okay. And then I can bring this term over to the other side, so I have m1 plus m2 a sub x equals, so now I have this minus, so m1 minus m2 g. Oh, let me rewrite that. m1 plus m2 a sub x equals m1 minus m2 g. So then I can just reorganize that, and I get a sub x equals m1 minus m2 over m1 plus m2 times little g. Oh, that's kind of interesting, because you look at it and you say, well, if m1 equals m2, then the acceleration is 0. Well, that makes sense. If I make the 2 masses equal, it's not going to accelerate. And then if you say, well, if I make m1 a lot bigger than m2, then it'll accelerate a lot. In fact, if I make m1 gigantically bigger than m2, it'll just drop at g. That kind of makes sense. And I guess if I make the masses big, but the mass difference pretty small, then I'll get a pretty small acceleration. So that's all pretty interesting. And what I did on the next slide is not any more interesting than what I did on the board. So I showed you how I wrote down 2 equations and 2 unknowns, and I solved them, and I got this same result here. And then, right, if m2 equals 0, so you just disconnect this mass, then a sub x is g. It's just like picking up m1 and dropping it. Okay, and if m1 is about the same as m2, then the acceleration should be much smaller than g. So it's like a small difference divided by a large sum. I happen to set up this machine so that m1 is 4.03 kilograms and m2 is 3.73 kilograms. So plugging in those numbers, we get the acceleration is 0.38 meters per second squared. That's a lot smaller than g. What is that? That is about 4% of g. So, and then you say, how long does it take to fall 2 meters? How long does it take m1 to go down by 2 meters? So you say, okay, x final is x initial plus v x initial t plus 1/2 a sub xt squared. So we're going to start out at x equals 0, let's say, and we're going to start out from rest. So we'll cross off these two. So we say 2 meters is 1/2 a sub xt squared. And that gives us time is 3.2 seconds at constant acceleration of 0.38 meters per second squared. Let's see how we do from the video clip. So I will add 300 grams to M1. So M1 will be 4.03 kilograms. M2 will be 3.73 kilograms. So we'll go from 0.7 meters to 2.7 meters, and we'll measure how long does it take M1 to fall from 0.7 meters to 2.7 meters. Here we go. Boom. And we can do it again. Go. Boom. We'll do this one more time with M1 at 4.03 kilograms, M2 at 3.73 kilograms. Okay, just to see the symmetry between M1 and M2, let's do the same thing on the other side. So I'll put 300 grams of added mass on the M2 side, and we can lift this up. So, let's move the block over so we'll hear the nice thud. So we'll start at 0.7 meters and we'll end at 2.7 meters, and we'll see how long it takes. So here we go. Go. Boom. Okay, one more time. Go. Boom. Okay. By the way, we could have also, if we'd wanted to, we could have solved for the tension when we had those two equations in two unknowns. We would have got the tension as 2 times m1 times m2 times little g, and then divided by m1 plus m2. You say, what does that mean? Well, if m2 equals m1, then this should be just the tension equals mg. Let's see if that works out. So that's like 2m over, and the m plus m is 2m g. Yeah, see, that's just mg. So if m1 equals m2, then you just get mg. That makes sense because we had the two blocks just sitting there not accelerating, and the tension in the rope was mg when we first considered the case where the two masses were equal. Now, what if m2 is very small? If m2 is very small, then we can cancel it out when it's added to m1. So then, this is if m2 is much less than m1. So m2 is kind of like epsilon in calculus. So then this would be like 2 m1 m2 divided by m1. So then the tension would be approximately 2 m2 g. And what is that saying? Somehow it's like approximately twice the weight of the small object is the tension. Oh, and I think, that actually kind of makes sense, because imagine, so basically the more massive object is basically just falling down at g. So then m2 is basically accelerating upward at g. So it's like it's being pulled upward in an elevator accelerating at g. So then its apparent weight, the force held by the tension, is its weight plus ma, you see? So this is kind of like, So this is like m, we've seen this expression before, a sub x plus g. So it's like accelerating upward at g, and then there's also its weight, mg. So that kind of makes sense also. It doesn't seem all that profound to me. But like, so if you make m2 much smaller than m1, m1 is going to just drop at g, and then m2 is going to just go up at acceleration g. And so then the tension is basically holding the lighter object's weight plus the m mass times acceleration to accelerate it. So yeah, it's like basically twice its weight. On an upcoming worksheet, you have a problem which is even a little more tricky than this Atwood machine. You're still going to write two equations and two unknowns. So you will draw a free body diagram for, I guess, so which direction is it going to go? I guess you have 2 units of mass here and 1 here. So I guess it's going to go this way. So we'll let our x-axis point this way, and we'll let our x-axis point this way. And you see, you're going to draw a free body diagram for this right-hand mass, which I guess will have the tension T pointing upward, and then 2 mg pointing downward. And then over on this left-hand side, you're going to draw a free body diagram that has the tension T upward and a single mg downward. And then there's also this spring force downward, which will equal the spring constant times however far the spring has stretched from its relaxed length. The positions of the blocks are adjusted until the spring is at its relaxed length. Okay, so then at the starting point, the spring is at its relaxed length. So at the starting point, the spring is not exerting a non-zero force. But then see, if they fall on a distance d, I guess the spring is exerting a force which is k times d, because initially it was a relaxed length. So d is the distance with respect to the relaxed length. So that's kind of interesting. So I guess you have tension up, and you have mg down, and you have k times d down on this side. And then you have 1 unit of mass, which is accelerating. And here you have 2 units of mass that are accelerating. So you're going to get 2 equations and 2 unknowns. One unknown is the acceleration in the x direction, and one unknown is the tension. And you solve for the acceleration. And won't that be fun? That's some cool algebra. Here is a much less complicated example. So I suggest draw a free body diagram for mass 2, then draw a free body diagram for mass 1, and assume that the acceleration is 0 for both masses. So we're going to work our way from the bottom up. Actually, when we later do structures, we'll do load tracing, working our way from the top down. But for something like this, where things are suspended from cables, usually you want to work from the bottom up. So let's try that. Let's draw a free body diagram for mass 2. So I'll call that mass 2 here. So we have downward a force gravitational by Earth on mass 2. So that is going to be m2 times g. Okay. I guess if I'm going to use g is approximately 10 newtons per kilogram, same thing as 10 meters per second squared, little g. So then I can do the math, then I can put in some nice numbers here. So this would turn out to be 10 kilograms, so that's 100 newtons. Oh, and then we have tension, TB. Okay, so, and if it's not accelerating, I think if it's not accelerating, these will be the same. So this is TB, which I claim, I would kind of look at this. So the way I usually look at this is it's like essentially the contact force by 1 on 2. If you don't see the rope as like a separate actor, it's just transmitting the force. And then let's draw, oh, and by the way, we were told that the acceleration is 0, so that's convenient. Then let's draw a diagram for number 1. So we have, I might offset it a little bit. So we have tension B downward on 1. Well, we know how big to make that. It's the same length as these other arrows. So that's the same length as that arrow. So this is tension B. But now from this perspective, it's like the contact force by 2 on 1. You see it points down instead of up. And then we have, here I'll draw it in a different color. We have, oh, this is also 10 kilograms. Whoops. Okay, so we have F gravitational Earth on number 1, which is M1G. And that's also going to be 100 newtons, I guess, because it's also 10 kilograms. And then we have TA, and I think this is going to be twice as long. So this is going to be A equals 0. And this is TA. Well, I don't know. I mean, I could call it the contact force by the ceiling on number 1, or I could call it by rope A on number 1. Okay, and now you actually know, since this happens to be, we were told this happens to be the same mass as this, so these happen to be the same. They don't have to be this. So, see, this is the same as this by Newton's third law, but this is the same as this because the two blocks happen to be the same mass. And they're not accelerating. So it seems like this must be, well, we know what this number is too. This, right. So you see, this is why you want to go from, so at the bottom, you see, we know this is 100 newtons because that's just the weight of block 2. So because this is not accelerating, we know this must also be 100 newtons so that the forces on number 2 here balance. So then we know that this must be 100 newtons because it's just the same tension in the same cable. And then we know that this is 100 newtons because we were told that the mass of that block is 10 kilograms. And then to make everything balance on number 1, since it's not accelerating, this must be 200 newtons. So I think we figured out that this is 200 newtons, and this is 100 newtons, the two tensions. I guess we'll see if we were asked for anything else here. Well, if you peek at the next slide, you can see my diagram for block 2. It looks like what I drew on the board. And then if you peek at the next slide after that, you can see that I drew out diagrams that look like the diagrams I drew on the board. And then I ask a kind of interesting question, which is, how would these two diagrams change if we imagine the ceiling is actually the ceiling of an elevator, which is accelerating upward at plus 2 meters per second squared, which is plus 0.2 g. So let's see how that would look. So if we were actually accelerating upward at 0.2 g, so let's say we have a sub x equals plus 0.2 g upward. So then we would, let's work from the bottom up. Usually works out that way. So A is 0.2 g upward. So if that's true for this diagram, then we have to make this arrow, and this isn't going to be true anymore. This arrow has to be longer. This arrow has to be about 20% longer than this arrow. See? So this is 100 newtons. So I think this will end up having to be 120 newtons. We can check that. I think this is what we're going to get. We're going to get that this is 120 newtons. And we'll check that in a minute. Okay, so then we don't know this right now. But then if that's right, then this will also turn out to be true. So this will also be 120 newtons. And this is still 100 newtons. This is still 100 newtons. So then this is going to be 0.2 g upward. And you see, I asked, how can you use these diagrams to write Newton's second law for each of these masses? So for mass 2, we're going to say m2 a sub x equals, so we're going to have our x-axis pointing up. And we'll say this is tension B minus m2 m2g. And that tells you that tension B must equal m2 times a sub x plus g. Well, a sub x is 0.2g, so 0.2g plus g is 1.2g. So that equals m2 times 1.2g. And 1.2g is like 12 meters per second squared, so this is basically, using g equals 10, this is 120 newtons. So that's what we wrote over there. Ha. Then, so this is accelerating upward at 0.2g. So what is Newton's second law? Let us write for mass number 1. Well, for mass number 1, we're going to say that m1 a sub x equals tension A minus tension B minus m1g. Okay, so that'll say m1 g plus a sub x plus tension B equals tension A. So then m1 g plus a sub x is the same as m2 g plus a sub x because they're both 10 kilogram masses. So this is 10 kilograms times 12 meters per second squared. So that is the same 120 newtons. That's 120 newtons plus 120 newtons. So this is 240 newtons. So actually, what does that say? So the results we got were the same as the results we got when it was not accelerating, except they're 20% bigger. So we accelerated upward at 0.2 g, and the two tensions became, each one became 20% bigger. Okay, nobody ever likes this question, but let's do it anyway. In the 17th century, Otto von whoever fitted two hollow bronze hemispheres together and removed the air from the resulting sphere with a pump. Two 8-horse teams could not pull the halves apart, even though the hemispheres fell apart when the air was re-emitted. Suppose he had instead tied both teams of horses to one side and bolted the other side to a giant tree trunk. In this case, the tension on the two hemispheres would be, So we're going to rephrase this as a cable, but the right answer is twice. It's twice. So basically, I think I have okay, here you have, let's suppose one horse, a team of horses. We'll replace a team of horses with a horse. So suppose a horse can pull 1,000 newtons. So then this horse is pulling 1,000 newtons to the right. This horse is pulling 1,000 newtons to the left. The tension in the rope is just 1,000 newtons. The acceleration of each horse is 0. Right. So there are two horizontal forces acting on horse A. The ground is pushing to the right and the cable is pushing to the left. On the left-hand horse, the ground is pushing to the left and the cable is pushing to the right. So both horses are pulling, they're not accelerating. The tension in the rope is 1,000 newtons, assuming each horse can pull 1,000 newtons. Now, suppose the tree stands still, and no matter how hard the horse pulls, this is just one horse, okay? So the horse is not accelerating, and the horse is pulling, and the ground is, so the horse is pulling with a force of 1,000 newtons on the rope. So that means the rope is pulling the other way with a force of 1,000 newtons on the horse. And meanwhile, the ground is pushing to the left with a force of 1,000 newtons on the horse. And then I guess the rope must be pulling on the tree with a force of 1,000 newtons. Therefore, the tree must be pulling on the rope with a force of 1,000 newtons. And the acceleration of this horse is 0. So it's 1,000 newtons of tension in the rope. So the two horizontal forces acting on this horse are the ground is pushing it to the left and the rope is pushing it to the right. Now I take two horses side by side and have them pull the same rope. Well, I think now there's 2,000 newtons of tension in the rope. So the horses are not accelerating, and you have the ground is pushing to the left on horse A, 1,000 newtons. The ground is pushing to the left on horse B, 1,000 newtons. So the rope is pushing horse A to the right 1,000 newtons, and the rope is pushing horse B to the right 1,000 newtons. So together, somehow they're tied together. Then there's 2,000 newtons of tension in the rope. I mean, maybe somehow you have to attach this rope to two horses. So maybe you see you've got the tree over here, and then there's like a horse here, and there's like a horse here. Somehow, like we're really talking about this tension, right? But somehow that tension has to be distributed to the two horses. So I think one horse can pull with 1,000 newtons, the other horse can pull with 1,000 newtons. So I think now you have 2,000 newtons of tension in the rope. So you've got this two-horse system pulling on the rope with a tension of 2,000 newtons, and the tree is pulling back with a force of 2,000 newtons. Nobody ever likes this problem. Then you say, well, what happens if instead of this tree, you have a third horse? So now you replace this tree with a third horse. Then, well, this horse, I'm calling this horse horse C, horse C loses his footing if he tries to pull more than 1,000 newtons. So you've got if the tension in the rope is 2,000 newtons, the force of the ground on C. So what does it mean that he loses his footing? You see the maximum force between the ground and the horse. Like what happens when you lose a tug of war? I think it's kind of like you get dragged on the ground, right? So the force between you and the ground isn't big enough to hold up your end. So I think the maximum force between the ground and the horse, the frictional force, is 1,000 newtons to the right. But meanwhile, you have 2,000 newtons to the left, and so then you have 2,000 newtons of tension in this rope. That means there's a 2,000 newton force by the rope pulling to the left on horse C, but there's only 1,000 newtons of friction from the ground pulling horse C to the right. Therefore, there's the vector sum of forces on horse C is 1,000 newtons to the left. So horse C accelerates to the left. That kind of makes sense. If the horse C is kind of losing this tug of war, so he's actually slipping and he's kind of being dragged to the left a little bit by these two horses. So that's kind of my two teams of horses. So you attach them to a tree, you get 2,000 newtons of force in the rope, and that's fine, and they can keep pulling. But you attach them to a third horse, and I think what happens initially is you get 2,000 newtons of tension here, and this horse slips and starts to accelerate. And maybe once he slips, then the friction force between him and the ground is even lower, so then maybe the tension then reduces a little bit. Nobody ever likes this example. So let's return for a minute now to the rope example from the first lecture. And you saw me hanging from the ceiling like this, and you saw me suspended from the ceiling like this, holding onto a rope. So we now have the tools to compare the first method with the second method a little more systematically. So we could draw a free body diagram for me for each of these two methods, method 1 and method 2. And let's say I'm not accelerating, so it's while I'm still hanging onto the rope before I let go. So in the first method, there's the force of the gravitational force by Earth on me, which is just equal to my weight. And then if I'm not accelerating, the other force on me is the contact force by the rope on me. So that's the force between my hands and the rope. So it just equals my weight. In method 2, we have the gravitational force by Earth on me. That's my weight going down. And then we also have the contact force by my friend on me. So I think from the earlier examples we've solved, as long as we're not accelerating, the contact force by my friend on me equals her weight. So that's my friend's weight, my friend's mass times g. That's my friend's weight down on me. And if I'm not accelerating, then the contact force by the rope on me has to be the sum of these two, so that all the arrows add up to 0. So that's the contact force by the rope on me is my mass plus my friend's mass times little g. So the force in the second case between my hands and the rope is the sum of my weight and my friend's weight. So you can see how much harder it is for me to hang onto the rope in that situation. So I think now we have kind of a quantitative tool for analyzing what we saw in our mind's eye on the first day of class. So we had our example here of the author's free body diagram. And one thing I don't like about his free body diagram is he's not careful to indicate what object he's drawing the free body diagram for. So in some places you will see that he has, for example, so when he draws his forces here, it's not obvious what object he's drawing a free body diagram for. And in fact, if you assume this is supposed to be the pre-failure situation where the deck is not accelerating, you can see we have, in this case, whatever these arrows are, they seem to add up to 0, but in this case, whatever these arrows are, they don't add up to 0, and it's because they're not all describing forces acting on the same object. And I think what he's really trying to compare is that the force between the nut and the rope is, for the upper deck, is 1 unit here and it's 2 units here. So he's trying to say this nut is holding its weight plus the lower deck's weight, whereas this nut is holding only its own weight. But when we draw free body diagrams, we try to be much more methodical about indicating what object we're drawing a free body diagram for. And when we draw forces, we try to indicate the force by what on what. Here's a problem similar to a worksheet problem you're going to do. So we could try to work through it to see how it works. So you can read the problem while I work on the diagram. So I'm going to start by drawing a diagram for M2. So here's my diagram for M2, because things are being towed, I always start from the back. And actually one more thing, do we know anything about the acceleration? I don't think we know anything about the acceleration. Okay, well, so this is A sub x is question mark, and this is a diagram for number 2, and we have backward, in the backward direction, we have this frictional force by the water on number 1. Oh gosh, this should be 2, this should be 1. Sorry. All right. So this is 1, this is 2. Okay, and this is 2. Okay, and then the other force acting on number 2 here is this tension B. So this is 4. We don't actually know the magnitude. Tension B. And that's kind of like, I mean, I would argue that's kind of like the contact force by 1 on 2, but you can call it whatever you like. It's basically the tension in that rope. Okay, so if you wanted to, you could then write Newton's second law, which says M2 A sub x equals TB minus FW2. Okay, this is this frictional force. So that's valid. That's Newton's second law for the second mass. And then let's draw a diagram for the first mass. So we're going to say, okay, here's the first mass. We don't know what the acceleration is, but it's the same as the acceleration of this one because the ropes are taut. So here we have TA to the right, and you can label it if you want to. You could call it like the contact force by the tugboat, which I called A for some reason on 1, but you don't even have to say that. And then going backward, we have tension B, And then going backward, we also have this frictional force of the water on number 1. So then we can write Newton's second law for the first barge. So that tells us m1 a sub x equals ta. Oh, I guess I should have said that this is the x direction, and I should have said in this diagram that's the x direction. It's good to indicate the x direction, so then you can say a sub x and you know that it's right minus left, or it's up minus down, or whatever your axis convention is. Ta minus Tb minus then the frictional force by the water on number 1. So I think that maybe, then the common acceleration of all 3 boats is a sub x. Let's see if we have enough information here then. So it seems like tension B is m2 a sub x plus this frictional force. And do we know the acceleration? I guess we don't. Oh, well, yeah, it is a sub x. Okay, yeah. So all this stuff is given. So I guess we can solve for tension B. And then down here we can say, what's tension A? So we can say tension A is tension B plus this friction force of the water on 1 plus m1 a sub x. And if I read the problem correctly, it seems like all this stuff is given. So the common acceleration of all 3 boats is given. And then we just solve for tension B up there. So we know tension B. And then I guess this frictional force exerted by the water, on this barge is given. And we know this mass, and we know the acceleration. So I think that's how you do it. You see, you draw a diagram for the back boat, and that lets you write down Newton's second law for the back boat. And then you draw a diagram, a free body diagram for the middle boat, and that lets you, after you enumerate all the forces, write Newton's second law for the middle boat. And then I think with the given information, we can go through and solve for the 2 tensions from the given information. Here is a variation on a worksheet problem. So you can read the text, but basically we have a blue cart, and resting up against it is a green cart. And then there's a red cart over here, and there is an initially relaxed spring of spring constant K over here. So the spring initially is relaxed. And then we're pushing to the right on the red cart. And the first question is, what is the acceleration of the 3 cart system's center of mass? And I think these are all on a low friction track. So friction is negligible. So you know that the m total of the system times a sub x of the center of mass of the system is the sum of the external forces. So if we draw a free body diagram for the system as a whole, listing only the external forces, actually you see this spring is an internal force, and this contact force is an internal force, and there's no friction. There is only one external force, and that is this force that you are exerting on the red cart. So therefore, the acceleration of the center of mass of the system as a whole must just be this external force that you are exerting on the red cart divided by the total mass of the system, which is m red plus m green plus m blue. So see, so we don't need to know anything about what this spring is doing or what's happening here to know how the center of mass of the system accelerates. So that's kind of interesting. That's sort of useful. The second part of the question is, what is the acceleration of each cart the instant you first begin to push? Oh, so that could be kind of interesting. So let's think about that. So the instant when I first begin to push, the spring is not compressed at all. It's at its relaxed length. Therefore, there is zero force exerted by the spring. So if I want to draw a free body diagram for the red cart, the instant that I first start pushing, then there's basically just this force that I exert on the red cart, and that is it, because this force is zero. So then I guess we would say A sub x of the red cart is just this external force divided by the mass of the red cart. And this is the x component, I guess. The acceleration of this cart and of this cart must both be zero because there's nothing pushing on them, because the spring isn't compressed yet, so this force is zero. So B is not too bad. Now this seems tricky. What is the acceleration of each cart the instant when the spring is compressed at distance d with respect to its relaxed length? Well, in that case, I guess the force exerted by the spring is k times d in magnitude. So it's pushing back on the red cart and it's pushing forward on the green cart. So let's see what the implication is for each cart. Let's start with the red cart, since we already have half of a free body diagram. So then it seems like the spring is going to push backward. This is the contact force by the spring on the red cart, and its magnitude is kd. So now we can say m red A sub x of the red cart equals right minus left. So I guess we'll say the x-axis goes this way. So this is the push that you are exerting on the red cart, the x component, minus kd. So, okay, that wasn't too bad. What about the green cart? So if we consider the green cart, so here's green, then it seems like for the green cart, we have pushing to the right is this contact force by the spring on the green cart, which has magnitude kd. Yes, so the spring is pushing to the left on the red cart, it's pushing to the right on the green cart. And then the other thing pushing on the green cart is this contact force by the blue cart on the green cart. But we don't know what that is yet. So, okay, so then I guess we could write Newton's second law. We could say m green A sub x green equals, that's the x-axis, kd minus this contact force by the blue cart on the green cart. That's not very satisfying, so we can actually do quite a bit better. So if we next work on the blue cart, in fact we should have worked on the blue cart before the green cart, so let's work on the blue cart. So the blue cart has only one force acting on it, and it is to the right, assuming that these things stay touching each other. So this is the contact force by the green cart on the blue cart. So now if we write Newton's second law for the blue cart, we get m blue A sub x blue equals, and then it's right minus left, is nothing to the left. So that's F contact green on blue. So that tells you that F contact green on blue is just m blue A sub x blue. So that's helpful, because now we can say this just equals kd minus m blue A sub x blue, because we know the magnitude, well, see, the contact force by green on blue is the same size as the contact force by blue on green, It's just that this one points to the left, while this one points to the right. So you see, this is the same force, but this copy of it points to the right, this one points to the left, because they're an interaction pair. There's one more thing. If these two carts are touching and they stay touching, then their acceleration will be the same. So you know that A sub x blue equals A sub x green. That's not necessarily the same as A sub x for the red cart, but the blue and green cart should have the same acceleration since they're touching, as long as they stay touching. So in that case, yeah, so in fact, let's just call this A sub x blue green. So then we can say that m green plus m blue times A sub x blue green is just kd. And so that is enough information to solve for A sub x blue green. Good. And then meanwhile, you knew what everything was acting on the red cart, because you knew kd, and you knew how hard you were pushing on the red cart. So you could get the acceleration of the red cart. So we were able to do part C as well. I did it with kind of abstract variables instead of numbers, but I think you'll get the idea. So you draw a free body diagram for each of the masses, and well, first you did it for the system as a whole. You could do the center of mass system as a whole. That requires only considering the external force. There's only one external force here. Then, if the spring is not compressed at all, then there's no force exerted by the spring. It's zero. So then the only thing with the non-zero acceleration is the red cart. So you can figure that out from a free body diagram for the red cart. And then and these are zero acceleration. And then in part C, we said, okay, we know how big this force is exerted by the spring. So you could draw a free body diagram for the red cart. That gets you this minus this. And then, well, actually, maybe the easy thing to do is you draw a free body diagram for the green-blue system together. And the green-blue system together, it's the sum of the two masses times its acceleration. And there's only one force pushing on this green-blue system together. And that is this k times d to the right. So maybe what I should have done for part C was, I was fine what I did for the red cart, but I should have solved for the green and blue carts together as a system, adding up their masses. And then there's only one external force acting on that system. You see, so this internal force between the green cart and the blue cart is kind of irrelevant for the problem. If you are smart enough, which I wasn't, to combine the green and blue carts into a little mini system. Estimate the spring constant of your car springs. Experiment. Sit on one fender. Well, I'm going to guess that if I sit on one fender, that one spring is going to compress, I don't know, maybe 5 or 10 centimeters. Let's say it's going to compress 7 centimeters. 0.07 meters, and I say that because I think my mass is about 70 kilograms, so then my weight is like 700 newtons, so newtons per meter. So I'm going to say that my spring constant is something like 700 newtons. I apply a 700 Newton force, I sit on it, and I think it compresses, I don't know, 5 or 10 centimeters. So let's say 0.07 meter, and that allows the 7 to cancel. So that's like 100.01. So that's like 10,000 newtons per meter. Okay, or you could call it 10 kilonewtons per meter if you wanted to. So it seems like, or you call it 10 to the 4th newtons per meter. You could also say 10 to the 4th newtons per meter. So I think, so there's 7, so it's like 700 divided by 0.07 is like 100 divided by 0.01. That's like 10,000. Yeah. So, okay, kind of silly example. I think you should go, sometime when you have a car that belongs to you or to a friend, you could give this a try. But I think it's going to be something on the order of 10,000 newtons per meter. When a 5-kilogram box is suspended from a spring, that spring stretches 1 meter beyond its, relaxed length. Oh gosh, this should have said relaxed length. In an elevator accelerating upward at 0.98 meter per second squared, that's 0.1 g, how far will the string stretch with the same box attached? So I'm going to tell you, my intuition says this is going from 1g to 1.1 g, so it's going to be 10% more stretching. So instead of 1 meter, it's going to be 1.1 meter. So I think this is what we're going to get. But let's see if we can work that out more systematically. So when we're just not accelerating, here's a free body diagram for the box. There's a downward force, which is the box's weight exerted by Earth on the box. And then there's an upward force, which is the force exerted by the spring. And if we're not accelerating, those two must balance. And the magnitude of this spring force is the spring constant times 1 meter. So in principle, that lets us figure out what the spring constant is. Then we can draw a free body diagram for the case where the box actually is accelerating upward. So it's the same box. But now we have A is 0.1 g upward. Is it upward? Yeah, upward. So this force will still be the same. The gravitational force, this force will still be the same. The gravitational force by Earth on the box is still the mass of the box times g, but now this arrow will be longer so that we accelerate upward. And this is the contact force by the spring on the box, which is k times some unknown value d. And so now we can be super systematic about it if we want to. So we can say, in this case, what does Newton's second law say? It says, we're going to have our x-axis point up. Okay. Let me try to be a little neater. So we will have our x-axis point upward, and Newton's second law for the box in this case says the mass of the box times a sub x of the box equals, up minus down, k times our unknown distance minus the mass of the box times g. So that gives us k times our unknown distance is the mass of the box times a sub x plus g. And this actually gave us that k times 1 meter is the mass of the box times g. So this actually is the mass of the box times 1.1 g. And right, this is the mass of the box times 1 g. So I think you could actually divide one equation by the other. If you divide one equation by the other, so you will get kd divided by k times 1 meter, and that equals mass of the box times 1.1 g divided by the mass of the box times g. So you see, that gives you d over 1 meter equals 1.1. There you go. So you get that the amount that the box stretches on the elevator. So on the elevator, it's going to look like this. So this is D with respect to the relaxed length. So D is 1.1 meters because you have to account not only for mg but also for ma. So it's like mg plus ma, and a is a tenth of a g. That was probably a little bit tricky. That is all I have for chapter 8, so I will see you in class. But we got 1.1 meter for this result.